Okay, the final property of transition metals to know about is that transition metals form what are known as complexes, and then that these complexes tend to be colorful. So what are these transition metal complexes? So it comes from the idea that the transition metal ions have a relatively high positive charge density. So as opposed to something like the alkali metals where you've got like a lithium plus or a sodium 1 plus, the transition metals typically form charges of 2 plus or higher. So things like copper 2 plus and things like Fe3 plus, for example. So transition metal ions have relatively high positive charge densities. And that means that they're going to attract things towards them which are negatively charged or electron rich, things that have extra electrons or just lone electrons, non-bonding electrons. So that's where this topic of complexes comes from. Now, it's kind of just an extension of something that we've looked at before, which is called an ion-dipole interaction. So we've talked about briefly that when you have things like salt dissolving in water, the polar water molecules are going to orient themselves in a way where the partial negative charge of the oxygen atom is near the positive charge of the ion. So, and if we had a Cl minus ion here, then the positive charge of the H, the partial positive of the H would align itself near the negatively charged ion. And so those interactions are known as ion-dipole interactions. Now, this is sort of an extension of that, or it's starting with that idea and then going further. So I'm going to erase it now so that it doesn't confuse us. In this topic, the charge density, the positive charge of the transition metal ion is so high that when something like water gets near the copper ion, instead of just aligning itself, the oxygen end aligning near the copper ion, one of the electron pairs of the oxygen actually gets donated and actually forms a covalent bond with the metal ion. So again, it goes beyond just the partial negative aligning and attracting to the metal ion, and now we're actually forming a covalent bond. And when a covalent bond is formed, where both of the electrons come from one of the atoms, we call that a coordinate covalent bond. We've seen that term before. This is now a new setting for this coordinate covalent bond. So when you have transition metal ions, they tend to attract things towards them that have non-bonding or lone pairs of electrons. And those lone pairs of electrons tend to get donated to them in the form of coordinate covalent bonds. And then what you end up with, if we look down here, and again, this goes beyond water. This first example I mentioned was water. You can imagine having copper ions in a solution, in an aqueous solution. So water is one thing, one substance that will form these coordinate covalent bonds to transition metal ions, but it's far from the only one. The example shown here shows ammonia molecules. Ammonia molecules are NH3. They also have lone pairs of electrons. And this N is partially negative. So again, it's a little bit like the ion-dipole interaction. But instead of just being attracted to the copper ion, the lone pair is actually fully donated to form coordinate covalent bonds. And in this example, we have 4 ammonia molecules all donating their electron pairs to the copper ion. And the result is that they form this particle. And this particle is what's known as a complex. Or specifically, this one is a complex ion. Now, it's not that different from a polyatomic ion, but the complex ions, we tend not to call them polyatomic ions. They're a little bit different. They have these transition metals at the center, and then rather than just having single atoms like oxygens radiating out from the center, they tend to have these other structures around them that can be full molecules like ammonia or water, for example. So it's a little bit like a polyatomic ion, but not exactly the same. So we're going to keep it as a distinct topic. So this particle where you have a transition metal at the center, and then it's covalently bonded to multiple species around itself, That's what is a transition metal complex. Now, these things that attach to the transition metal, we give them a name. We call them ligands. Ligands are species, and I use the term species because it could be an ion, it could be an atom, it could be a molecule. So different things can act as ligands. So we say they are species with at least one non-bonding electron pair, and they need that so that they can form coordinate covalent bonds with a metal ion. This list here is in the data booklet. The list of common ligands is in the data booklet, and eventually we'll talk about why they have these greater than symbols, but that's not for right now. Now, many of them are single monatomic ions like I-, Br-, S2-, those are just a single atom. Some of them have two atoms like hydroxide. Looks like this. Water, we know what water looks like. But the important thing is that we can draw them and that we can draw their lone pairs, because that's part of the definition of what makes a ligand. If you were asked to draw one of these things, you would definitely want to focus on the lone pairs that are on them, like CN cyanide looks like this. Carbon monoxide looks like this. And SCN-, you can draw it a couple different ways, but this is one way that we could draw it. Okay, so we have lots of different ligands, but they all have something in common, which is that they all have at least one lone pair, and many of them, you'll notice, have a negative charge. So they're sort of electron rich. They've got these unbonded electrons. In many cases, they have an extra electron or two, and that's why they are attracted to these highly positive, highly charged, dense transition metal ions. And so a complex is when you have a transition metal ion that has a bunch of ligands that bond to it with these coordinate covalent bonds, and that's what's called a complex. If it has an overall charge, we can call it a complex ion. The way that the formulas get written for complexes, they tend to put the complexes in brackets, so like this. And so it's going to be important as we approach this topic, that you can see the different ligands. The ligands get put next to the transition metal, and they get put there in parentheses. So this is a complex that has one cobalt ion at the center, and then it has 6 NH3 ligands. So that's how I interpret that, and the fact that it's all in these brackets means that that's the complex. So the complex is this cobalt in the middle, and it must have 6 NH3s coming off of it. I'm just drawing the ends right now, but then there'd be H's coming off of these things, like that. So that's what that complex is. And the whole thing has a charge, so I could put it in brackets and put 3+ on the outside. Okay. Now, this one is a copper ion at the center, surrounded by 4 Cl- ligands. And over here, it looks like I have iron at the center. It has 3 water ligands and 3 cyanide ligands. So you can have more than one kind of ligand attached to the same metal as part of the same complex. It's all possible. Okay, now a very common question, and what I was going to get at before, is that it's very important to know which ligands have charge and which ligands don't. Now, almost every ligand in that list has a -1 charge. There are 2 important exceptions, water and ammonia. Those come up a lot, and those are both molecules, so those both have 0 charge. So H2O and ammonia ligands have 0 charge, whereas most of the other ones are minus. So a fairly common question is, given the formula, you need to try to figure out what is the charge on the metal ion, or they might refer to it as the oxidation state. For now, we're just going to think of that as what is the charge on the metal ion. So if I look at this one, I can see that the overall charge is 2+. Then I break down the formula. There's 1 cobalt, and there are 6 H2Os. I know that the 6 waters are all neutral, so they aren't contributing anything to the charge. So all of the charge, all of that 2+, must come from the cobalt. So for the cobalt, we say it has a +2 oxidation state, or a +2 charge. So the charges of the ligands and the metal have to add up to the overall charge on the ion. So here we go, copper and Cl4. Overall, 2-. I'm not sure what the copper is, but I do know that chlorides each have a 1- charge. So I've got 4 minuses here. They have to add up to 2-, so the copper must have +2 as its oxidation state to balance out 2 of the minus charges. Okay, come down here, just to show a slightly different kind of question. This one was silver in it. Now, they've put the brackets here. So this part in brackets is the complex, or the complex ion. This is just another ion. Now, I know that's a bit confusing. What that means is that the Ag is bonded to the NH3 through covalent bonds. And then overall, that's acting like a big particle. This is the complex ion. So what's the Cl doing there? Well, the Cl is a different ion, and they must be interacting through ionic bonds. So that's what's keeping them together. And really, the ionic bonds are between them, the ionic attractions. Okay, so we can use that idea to figure out the charges. I know that Cl is a 1- ion, and that means that this complex ion here must have a 1+ charge to balance out the 1- charge of the chloride ions. So we still follow our rules about ionic compounds here. If chloride is 1-, then the positive ion must be 1+, since they are in a 1-to-1 ratio. So then, that's the charge on the complex ion. Then I can look inside the complex ion to realize that ammonia is neutral, and therefore the 1+ charge is coming from the Ag. So the actual oxidation state, the charge on the silver, must be +1. Okay? So that's the premise of figuring out charges either on the whole complex ion or on the transition metal inside of it. You need to be pretty familiar with the ligands, what charges they have, if they're neutral or not, and then being able to add up charges, balance them, and so forth. Okay. Then complexes can have different shapes. Thankfully, we are already familiar with these shapes from VSEPR theory. So the ligands tend to add in 2s, 4s, or 6s. And it depends what the ligands are, what the metal is. Different ligands take up different amounts of space, so they attach to these metals in different numbers. But 2, 4, and 6 are the common numbers of ligands that tend to bond to a given metal ion. Well, if there are 2 ligands, we can say the coordination number is 2, and the shape, the geometry, is linear. When we have a coordination number of 4 ligands, there are actually 2 shapes that we know about, square, planar, and tetrahedral. Now, there's not really a good way that you could distinguish whether or not something's going to form square, planar, or tetrahedral. So if you were asked this on a test, I would probably lean towards guessing tetrahedral, and you'll probably be safe with that. It doesn't come up very often. The last one is when you have 6 ligands, a coordination number of 6, then we get the shape of octahedral. And this is probably the most common combination that we see. Most of the complexes that we look at have 6 ligands. Some have 4, a few have 2, but 6 is probably the most common. So octahedral complexes are quite common. Okay, final bit about complexes. Those ligands, all the ones that we've looked at so far, each ligand forms a single coordinate covalent bond with the metal ion in the center. So here's the iron, and each water molecule, each water ligand is just forming one bond with the ligand. But there are things known as polydentate ligands, so many teeth ligands, so ligands with many teeth. And really what that means is it's ligands that have more than one non-bonding electron pair, more than one lone pair, and a big enough geometry that they can actually form more than one coordinate covalent bond with the same metal ion. These show up in biology. For example, this is a representation of the protein hemoglobin, which carries oxygen around in red blood cells. And on each part of the protein, there are these heme groups. And if you actually look at the structure of a heme group, there is a transition metal ion at the center of iron, and there are nitrogen atoms around it, and each one of these ends forms a coordinate covalent bond with the iron. But those ends are part of the same molecule. So this one giant structure here is forming 4 coordinate covalent bonds with the same ion. So the heme group is an example of a polydentate ligand. Okay, that's a more complicated example than you need to worry about for the core syllabus. The data booklet gives you a couple of molecules that act as polydentate ligands in table 16. I've rarely ever seen this topic asked about. You would just look for how many bonds do you think this ligand might form. Well, these ones, you've got the 2 ends, so this one could probably form 2 coordinate covalent bonds. That's really all that it has going for it. This one, ethane dioate, has these 2 oxygens that are negatively charged with these extra electron pairs. So these are the 2 oxygens that are likely to form coordinate covalent bonds to the same metal ion. These other O's are pointing outwards in the opposite direction, so they can't also form coordinate covalent bonds to the same metal ion. And then you have this crazy thing called EDTA. This one can actually form up to 6 coordinate covalent bonds by itself. And there's a picture of it doing so down below. And as you can tell, it gets pretty darn complex. So you've got each of these O's can lose a hydrogen and do it, but also these N's can form coordinate covalent bonds as well. So polydentate ligands are a very minor sort of offshoot of the complex topic. You kind of need to know that they're possible, but I wouldn't worry about them beyond that. But being able to look at the formula of a complex or a complex ion and determine geometry and determine charge on the ion or on the metal is a very important topic.